Good morning. This lesson is for my Honors Integrated 1 class, but before I get started, I want to say I hope that everyone is doing all right out there. So this lesson is in place of what's in the book for section 14.3. I feel that since this is a section that deals with repeated multiplication or repeated division, it would actually be worth looking into the behavior of those operations. Now, we probably feel that we know everything about multiplication and division, and you probably do. It's just probably, you're aware of it, it's just never been formalized. And I'd like to use this lesson to nail down a couple things about multiplication and division that are going to be very important in moving forward. So let's talk about our 3 goals today. Our first goal is going to be to discover a behavior for division. We have certain assumptions about division and multiplication. Maybe most of you do, some of you don't, but we have certain assumptions. I'm going to relate the discovery that we found on the behavior for division to multiplication, and then after that we're going to go back and we're going to revisit rewriting tables with patterns. Now, geometric meaning is multiplication or division, so we're going to rewrite tables with patterns using multiplication and division. We did that already with addition and subtraction, so hopefully in this part of the goal seems to be very familiar from our prior experience. All right, our first goal. I'm gonna tell a story. I'm gonna make an analogy about division. I'm gonna talk about something that behaves like division, and hopefully through that you understand the behavior that I'm trying to accomplish. All right, so the act of scooping, I think I spelled that wrong. I don't know how to spell, so I'm going to put a red line under this to indicate that that's spelled wrong. I think there's one P in there, but I don't know. Whatever. The act of scooping ice cream represents division. The act of scooping ice cream represents division. Imagine that we have a tub of ice cream that would be emptied with 100 scoops using a normal size spoon. So this tub of ice cream right here, I can take 100 scoops with my normal size spoon and it's empty, okay? So I have 2 spoons, a larger spoon and a smaller spoon. And so if this spoon can empty this tub, doing 100 scoops, remember this is the act of dividing, scooping. If this spoon can empty this tub with 100 scoops, how many scoops do you think this spoon would need to empty this tub of ice cream? How many scoops do you think this spoon would need to empty this tub of ice cream? Think about it for a second. I'm sure some of you are thinking like, okay, I have a number, it's going to be half because it's twice as big. That's probably a pretty good assumption. But I think we can all agree that this is going to take less scoops, because every time you scoop, you're taking more. All right, so I'm going to write down under this, under the larger, let me learn how to talk. I'm going to write down under the larger spoon that we will need less than 100. I think we can all agree on that. It's going to take less than 100 scoops. Okay, this is going to take less than 100 scoops. And the normal spoon from the earlier is going to take 100 scoops. And the little spoon, I think we can agree that it will take more than 100. Now, you might have thought of a number like, oh, it's going to be 200 because it's half as large. I mean, that's reasonable, but we don't know for sure if it's exactly half the size. But we can say for sure that it's going to take more than 100 scoops, right? And this hopefully gets you to understand the behavior for division that's been there the whole time, but maybe we just weren't quite aware of it. So this spoon when we use it, we get a result that's smaller, right? And so for a lot of us, we assume that division makes things smaller. That is something that we assume, right? Division makes things smaller. Makes numbers smaller. Right? That's our probably the most common preconceived idea when it comes to division. That when I divide, I'm going to get a smaller result. However, we see that if we are using a smaller spoon, we get a larger result. So this is a new behavior that I wanted to focus on, discovering a new behavior. That dividing can make numbers larger. That is a new behavior. That is what the first goal was trying to accomplish, to get you to understand. Dividing can make numbers larger, right? That is a behavior that I believe that you're not aware that division can do. Now, when you guys get to higher level mathematics, you're going to start to ask this question, what happens when the spoon gets really, 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 really big? And you're also going to ask yourself the question, what happens when the spoon gets really, 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 really small? I'll stop with that because I can go on a complete tangent on that. But anyways, this is a key concept, that division can make numbers larger. And so this analogy for division, these spoons actually do represent numbers. Now, the normal spoon is actually the number 1, okay? The large spoon are numbers that are larger than 1, okay, bigger than 1. The smaller spoon are numbers that are smaller than 1. Oh, let's see. How do I write this? These are numbers smaller than 1, right? But they're also numbers that are bigger than 0. We're only dealing with positive signs of numbers. So the small spoon are numbers between 0 and 1. The normal spoon is equal to 1. And the large spoon are numbers larger than 1. Okay? So I'm going to go ahead and check off our first goal. Discover a behavior for division. Division can make numbers larger. Moving on to our second goal, I think we can accomplish this with a table. Remember, multiplication and division are opposites. We consider them opposite operations. So I'm going to fill in the size of the numbers. Numbers that are bigger than 1. Number that's equal to 1. And then the last size of numbers are between 0 and 1. There we go. There we go. All right. So when I divide by a number bigger than 1, my result is going to be smaller, right? So we get a smaller result. L. When I divide by a number that's equal to 1, I get an equal result. And when I divide by a number between 0 and 1, I get a larger result. So division has 3 behaviors. It can make numbers smaller, it can make the number equal, or it can make the number larger. And remember, multiplication is the opposite. So if I multiply by a number bigger than 1, we're going to get a larger result. If I multiply by a number equal to 1, we're going to get an equal result. Okay? I write my letters different every time. Huh. And if I multiply by a number between 0 and 1, I'm going to get the opposite, which is a smaller result. So I wanted to use this story about scooping ice cream with 3 different spoon sizes to show you that we get 3 different behaviors. And then I wanted to relate that to multiplication, because multiplication and division are opposites. So again, if I multiply by a number larger than 1, I get a larger result. If I multiply by a number that's equal to 1, I get an equal result. And if I multiply by a number between 0 and 1, I get a smaller result. This is very important. Okay? And I'm sure that goes against what we assume. Multiplying always makes numbers larger. If I multiply 10 by a half, which is between 0 and 1, I'm going to get 5. If I multiply 10 by 2, I'm going to get 20, which is a larger result. If I divide 10 by 2, which is a number bigger than 1, I get 5. I get a smaller result. If I divide 10 by 1 over 2, or 0.5, dividing 10 by 1/2 means I get 20. I get a larger result. And we'll talk about how that works in a little bit. But I'm going to go ahead and erase everything and then come back and talk about our third goal here. So we'll be back in a second. Let me try that again. I'm going to erase everything and write everything else on the board for the second part of the lesson. So I'll be back. I'm back. All right, so here we are moving on to our third goal for this lesson. And I want us to be able to rewrite tables with geometric patterns. Remember, geometric patterns are patterns created by multiplication or division. And we just saw that multiplication can make numbers larger or they can make numbers smaller. That was the point of the first 2 goals. I'd like to start off our third goal by reviewing what we've already done. And in the first semester, we would rewrite a table with an arithmetic pattern. That's a real fancy way to say a pattern based on addition or subtraction. So I'm hoping that we remember what we've done in the past and we apply our skills that we've gained to the new idea, and we realize that they're very, very simple. So let's figure out how these are changing. 6 turns into 11 by adding 5. 11 turns into 16 by adding 5. And 16 turns into 21 by adding 5. So we're adding 5, that's our common difference. Now remember, when we rewrite a table, we write the first row exactly how it was. 0, 6. And we keep the x coordinates the same, so it goes 0, 1, 2, 3. So this goes 0, 1, 2, 3. And the other comment I want to remind you is whatever was our first y term, we write it in every row. So instead of saying 11, I'm going to say that I need 1 5 added to my 6 to go from 6 to 11. So I'm going to write it like this. 6 plus 5. To go from 6 to 16, I need to add 2 5s. So this becomes 6 plus 5 plus 5. And to go from 6 to 21, I have to add 1, 2, 3 5s. So this is going to be 6 plus 5 plus 5 plus 5. I want to write down a couple observations about this example that that we're going to use in our new idea, our new concept. The first observation is going to be that the first row stays the same. Our second observation is we use the first y value in every row. I should also point out this row 1 is still equal to 11. Row 2 is still equal to 16. and row 3 is still equal to 21. We want to write our numbers like this because when we do that, we're able to create, we're able to generalize a pattern, which means that we're going to be able to write an equation for this table. And so we want to get to a point where we see we have a pattern. Like here I have 3 5s on row 3. Here I have 2 5s on row 2. So hopefully we're remembering what we did first semester, because this is going to seem very familiar. I do have a couple things I want to talk about. Common ratio is the next y value divided by the previous y value. If n was 5, then this would be 5 minus 1, which would be 4. So this would be f of 5 divided by f of 4. So we would have consecutive y values with the latter being on top. I'll talk about this goal when I work out example 2, but let's just work on this. And let's first find our common ratio. So the common ratio would be the next term divided by the previous. So this common ratio, or the ratio from row 0 to row 1, would be 6 over 3, and that's equal to 2. To go from the row 1 to row 2, it will be the next divided by the previous, 12 over 6, that is 2. And to go from row 2 to row 3, it'll be 24 over 12, which again reduces to 2. So we have a common ratio, so we have a geometric sequence, or a geometric pattern, I'm sorry. It's not a sequence because we don't have a first term, we start with a 0 term. So we're going to use our observation. First row stays the same. All right, so this is 0, 3. Our x values stay the same as well. So 1, 2, and 3. And to go from 3 to 6, I multiply by 2 once. So this is going to become 3 times 2. To go from 3 to 12, I have to multiply by 2 twice. So this becomes 3 times 2 times 2. And to go from 3 to 24, I have to multiply by 2 3 times. So this now becomes 3 times 2 times 2 times 2. This is what I want the table to look like when we rewrite it using geometric patterns. All right, we'll talk about simplifying this on the next lesson, but I want us to be able to write it out like this. Do notice right now I have the same number of 2's as I do for that row value. So just like before, we'll be able to figure out what to do when it does not happen. So let me move on to example 2, and I would like to talk about this before we get into this problem, and it's how to rewrite a fraction over a fraction, because again, when we write the common ratio, we write the next y value divided by the previous, and notice I have 2 fractions, so we're going to get our fraction over a fraction. So real quick, in order to get rid of a fraction over a fraction, we technically multiply it by the number 1. And we're going to exploit the concept of any number over itself is equal to 1. So what I'm going to do is I'm going to take this fraction and I'm going to flip it and I'm going to write it over itself. And what ends up happening is this value cancels with that value, this value cancels with that value, and remember from a previous lesson that we multiply straight across. So now I get A times D over B times C, and this all turns into 1, and I can get rid of that 1, and I now have the following fraction. A times D divided by B times C. Now I do not have a fraction over a fraction. I have one fraction, and again I got rid of the fraction over the fraction by technically multiplying it by the number 1. Alright, let's see if we have a common ratio. So here I have 4 and 12, so it's going to become 4 over 12, which reduces down to, let's see, I can divide a 4 and a 4, it reduces down to 1/3. Here I have a 4 over 3 being divided by a 4. But I can call that 4 over 1, and basically what you saw here is whatever fraction was on the denominator, I can take it up and just flip it and put it with the numerator. So I can now say this comes up like this, and we can actually cancel out. Let me move this to the side. I'm going to need more space. So this is going to be equal to 4 over 3 times 1 over 4. Those will cancel, and now I'm left with 1 over 3. So far, I have the same ratio. Let's put this y value on top of this y value. I get 4 over 9 divided by 4 over 3, and that's going to be equal to 4 over 9 times 3 over 4. The 4's will cancel, and I'm left with 3 over 9, which reduces down to 1/3. So I do have a common ratio. My common ratio is 1/3, and that's a number between 0 and 1. When I multiply by a number between 0 and 1, I'm making a smaller number. That was the point of the first two goals. When you multiply by a number between 0 and 1, you get a smaller result. The values are decreasing, they're getting smaller and smaller. I need to see how much room I have on the screen. Ooh, not much room at all. I'm going to have to, I guess I can erase this. Where did I have my eraser? All right. So again, the first row stays the same, 0 and 12. I use the same x values all throughout. Let me do what I did before. It needs a different color in the table. Oh, you're okay. No. Now I'm being real nitpicky. All right. So 0, 12. The first row stays the same. I use all the same x values, 1, 2, 3. And let's see here. I use the first y value in all my rows. To go from 12 to 4, I have to multiply by 1/3. So this is going to be 12 times 1/3. To go from 12 to 4 over 3, I have to multiply by 1/3 twice. So this becomes 12 times 1/3 times 1/3. To go from 12 to 4 over 9, I have to multiply by 1 over 3, 1 over 3, 1 over 3, 3 times. So this becomes 12 times 1 over 3 times 1 over 3 times 1 over 3. So this is what your homework's going to be about, is rewriting the table with a geometric pattern, which means you're trying to get, you have to use the first y value in every row. You have to make sure that you have a common ratio. And you just tell me how many times you have to multiply by that common ratio to get to that row value. So I'm going to go ahead and end the lesson here. Again, I hope everybody is doing all right. Have a good day. Bye-bye. I'm going to get that right one day.